Nice simple one to get started with. Momentum P is equal to mv, right, the product of mass and velocity. Number 2 is called the law of conservation. Usually we just say of momentum, but if you're being really pedantic, it's linear momentum. We do angular momentum as part of advanced higher course. And it states that the total momentum after a collision is the same as the total momentum before. In the absence, and this is a bit people often forget, in the absence of external forces, i.e. no friction, right, no gravity, no weight. And then our number 3 is carry out calculations. So I'll do a couple of worked examples. So in the first worked example, we're looking at ones where the cars don't stick together. So we've got car 1, which is a mass of 1200 kilograms and is moving at a speed of 10 meters per second. Car 2 has a mass of 1000 kilograms. All of this was given in the original question and is moving in the opposite direction at 8 meters per second. So that's our before situation. I should have put that up above that, right? And then after, we know they've stuck together. So we've got 2 of them stuck together, which is 2200 kilograms. And we don't know what speed we're going at, so we'll assume it's to the right. I'll take that as positive and just call it v, or unknown. So let's write that over here. Be clear about your directions. So split our page up beforehand. M1 times U1, U for initial speed, remember, 1200 times 10 is 12,000. M2 times U2 is 1,000 times, and we need to put that in as -8 to indicate the opposite direction. Okay, momentum, like velocity, is a vector quantity. And therefore total momentum before and we're just doing a simple sum there, is 4,000 kilogram meters per second are the units of momentum, no special units involved. And then afterwards, right, our M, which is our combined mass, times our V is 2200 times V. So total momentum after and conservation of momentum tells us that total, I'll start using P, before equals total P after. So 4,000, and that is an important statement, that line above, because you're shown to the marker that you understand that momentum is conserved. And now we can just rearrange that to get our value of V, divide both sides by 2200 and give you the answer 1.8 meters per second to the right. And strictly speaking, to the right isn't required because it asked for speed in the question rather than velocity. But good idea to put it in. And an example now where they don't stick together. So Making clearer directions, we've got our before and after. And some of the information isn't given in the question, it was actually given in a diagram. But once again, just going to practice drawing our diagrams for ourselves. So we had a 1200 kilogram car moving at 12 meters per second, and it hits an 800 kilogram car moving at 9 meters per second. And afterwards, we don't know what the 1200 kilogram car is doing, so we just give it a letter and we'll call it V1. But we're told in the question that the 800 kilogram car, not surprisingly because it's just been hit from behind, has sped up to 11 meters per second. And now put a line down the middle of our page and start doing our before and after calculations. So M1U1 is 1200 times 12. M2U2 is 800 times 9. Everything in the same direction now. So our total momentum beforehand is 21,600. And now looking afterwards, the first one is M1V1, it's 1200 times V1, and that's all we can do with it, we can't take that any further. M2 times V2 is 800 times 11, is 8,800. So total momentum after is 1200 times V1 plus 8,800. So now we can bring both sides together. So 21,600 equals 1200 times V1 plus 8,800. Subtract the 8,800 from both sides, and that will give you 12,800. And then divide both sides by 1200. I'll put that on another line actually. And I'll also give it to 3 significant figures. And once again, I don't really need the direction because this particular one asked me for speed. But get into the habit of putting it in because usually it does ask you for velocity. Okay, learning outcome 4 defines an elastic collision. And that gives us as one in which both momentum and kinetic energy are conserved. So momentum is basically conserved in all collisions in the absence of net external forces. But what we find is that kinetic energy, now energy, the total energy will be conserved. We've met that in the previous chapter, total energy. Conservation of energy tells us total energy remains the same. But here we're looking specifically at kinetic energy. So energy can change form, but what we're saying was in a perfectly elastic collision, no energy changes form. Okay, and the total kinetic energy is the same before and after. And it might sound a bit idealistic, but it can happen when you're looking at collisions between atoms and stuff like that. Which friction wouldn't be important and so on. An inelastic collision is one in which momentum is conserved. So it's conserved in both of these. But the total kinetic energy decreases. So you've not got total kinetic energy remaining the same. Some might get lost due to heat and sound. But even if you didn't have friction, often when you get things which stick together, then you can get these energy losses. Energy is converted into bonding the two things together. It can be a bit dangerous. If two objects stick together, then that will always turn out to be an inelastic collision. If they bounce off each other, it won't necessarily be elastic. And basically, you'd have to prove it in either case when you look at the questions that you tend to get asked. So you need to start questions based on those by assuming momentum is conserved, work out all the important velocities, but then work out the kinetic energies and show whether they're the same before and after. So although it doesn't say carry out calculations, I'll do a worked example of that next. So as this worked example, I'm going to go back to learning outcome 3, worked example 1. And that does show you the idea that you always start, you know that momentum will be conserved in any collision, so you start by looking at conservation of momentum and use that to get all the velocities. And then we can look at the kinetic energy before and after. So before, half mv squared becomes a half m1 u1 squared. So u1, remember, is just the speed before. So it's a half times 1200 times 10 squared, and the same m2 times u2 squared is a half times 1000 times, you can put in the minus if you want, but when you square it, it's not going to matter, remember, and that will give you kinetic energy before and after. And after, before for the two objects, and after we've just got a half mv squared, because it was just one mass, 2200, and we worked out that v was 1.8 squared. So we can now work out all these values. We get 60,000, 32,000, giving you a total 92,000 joules, and after we get 35,640 joules. So we can see that the kinetic energy has decreased. The collision is inelastic. Because the total kinetic energy has decreased. Now, for some bizarre reason, the SQ are very fussy that you say it's decreased, not just that it's changed, that it's different. It's not the same. Don't accept that. You've got to say the total kinetic energy has decreased. And if you had two separate vehicles after, you'd have to do two separate kinetic energy calculations and just add them up and check if it's the same before and after or not. Finding outcome 6 is another carry out calculations, and it's involving explosions. Explosions in physics mean that you start with an object which then splits into two parts. So for instance, for demonstrating a lab, you might start with two trolleys and use the plunger in between them for them both to push apart from each other. And then when you work out, just like all our collisions, then the total momentum is conserved. But actually explosions are much simpler because the total momentum beforehand is 0. So when we look at an example of this, we'll see the working's quite simple. So our before just becomes quite simple. Total P before equals 0. And then our after, okay, we have the bullets. Doesn't matter which you define to be going in which direction, but we'll have the bullet, which is 5 grams, moving at 100 meters per second. The gun is 1 kilogram, and it's telling us it's recoiled, so I'm going to put in the arrow for V going that way. So speaking, we'll call it V1. Let the other one be V2. But we'll need to make sure that we're clear that that should come out to be a negative value. So M1 V1 is 1 times V1. M1 is 1 kilogram. M2 V2 is 5 grams, which is 0.005 kilograms. It's our standard unit of mass. Don't actually need to put the unit in the middle of a calculation. You could write that as 5 times 10 to the minus 3 times 100 is 0.5. So total P after equals 1 times V1 is just V1 plus 0.5. So total P before equals total P after. 0 equals V1 plus 0.5, and you get V1 equals minus 0.5. So the recoil, that minus indicates the recoil, the opposite direction. I should actually have indicated at some point. That opposite direction then is indicated by the minus sign. So the recoil of the gun is 0.5 meters per second. In the opposite direction. Now I sincerely doubt that you will be asked to show this, but basically it's good kind of background knowledge. So if you've got two objects, hopefully by now you're getting the general idea, M1, M2, U2, and that's our before and after. And we're just kind of leaving it abstract now, so we've got no values involved. We don't actually know any of the values of these velocities, but we're going to do some algebraic manipulation. So the velocities before are called U1 and U2, and after are called V1 and V2. So the total momentum before is M1 U1 plus M2 U2, and it must equal the total momentum after, which is M1 V1 plus M2 V2. Now you're not expected to memorise that formula, but what I'm going to do now is to gather together the terms for object 1 and object 2. So we can gather together M1 U1 minus M1 V1, taking that term over to that side, and if we did that on the other side, you get M2 V2 minus M2 U2. And then gathering together some terms, I'm going to put M1 there, but I'm going to put a minus sign, and you get V1 minus U1 and M2 V2 minus U2. And basically what we're showing here is that the change in momentum for object 2 is negative the minus of the change in momentum of object 1. So basically whatever object 1's momentum increases by, object 2's will decrease, or vice versa. So the changes in momentum are equal in size and opposite in direction, because that's all a minus sign means in physics. equal in size and opposite in direction. And if we carry that forward, basically we can show that the forces are equal in size and opposite direction. That might have rung some bells, that statement there, because it's a wee bit similar to Newton's third law, and that's that the forces are equal in size and opposite direction. So whatever object 1 applies in object 2, then object 2 will apply an equal force in the opposite direction. So all that's missing in terms of our force formula here is the time. So I can divide both sides of this formula by time, and it will be the same time. You can't have a different time for one object as you do for another. However much time object 1 spends applying a force in object 2, then vice versa, object 2 will spend that same time applying the force the other way around. So I've divided both sides of what I had up here by t, and what I have now is minus m1, and that's the acceleration of a1 equals m2 a2, I minus the force on object 1 is equal to the force on object 2, and that is a statement of Newton's third law. So conservation of momentum and Newton's third law are entirely equivalent ways of saying the same thing. The forces acting on each object are equal in size and opposite in direction. Notice we don't just say equal and opposite, we need to be clear about what's equal and what's opposite. So it's equal size and opposite direction. Learning outcome 8, we're going to introduce another quantity, and it doesn't have any abbreviation, it's just impulse. And we define impulse as force multiplied by time. And the units of impulse then could be written as Newton seconds. Right, notice once again no per, we're very used to per second in a lot of units, but here it's not, because we're not dividing by a time, we're multiplying by a time. But if we think about the equation that we were looking at there during learning outcome 7, right, we were basically using F equals ma, and if we look at applying F equals ma, then we can write impulse equals m times a times t, but a can be written as v minus u over t, and then the t's cancel out and you're left with mv minus mu, which is change in momentum. So ft impulse is also equal to change in momentum. So we can see it can be a useful concept, because as we just saw a wee second ago by Newton's third law, that the impulse of object A on B will be equal in size and opposite in direction to the impulse of object B on A. But we'll also see much more useful ways to use impulse to explain some situations. And that's really what this next one's about, interpreting force time graphs for colliding objects. Now we kind of need to do 10 and 11 together, because impulse is the area under a force time graph. So up to now we've really just focused on area under a velocity time graph. And if you think about the equation d equals vt for constant speed, then basically if the speed is changing, then you use the area under graph of a velocity time graph. If impulse is equal to ft though, if f is changing, then you use the area under a force time graph to get impulse. And what we end up with is often we're looking at these kind of common situations, like why would you rather jump onto grass than concrete? Why do cars have bumpers? Okay, and basically in these kind of common situations, it's about taking the same impulse. So if you have to jump out a window because there's a fire in your house, the speed you're going at when you hit the ground is going to be the same in both cases, whether you jump onto concrete or jump onto grass. And therefore your momentum when you hit the ground is going to be the same, and assuming you come to a stop, your change in momentum will be the same. But by using this idea that impulse is ft, by controlling the time for the collision to take place, i.e. by jumping onto something softer like grass, which is a bit of give, right, then we can spread the impulse over a longer period of time, and that makes the force smaller. So basically, if you jump onto a hard material, you might have an impulse, a force time graph. It looks like that. So a short period of time resulting in a large force. Whereas if you jump onto a softer material, you get a similar shape of graph, but by spreading the calculation over a larger t, you get a smaller force. So the area under the graph in both of these cases is the same. So your change in momentum is the same, but by making the time longer, then you decrease the force involved. And that's why it's better to jump onto grass. And lastly, we just look at worked examples. So I'll do a worked example based on the calculation and one based on a graph. So here's an example I found online. I'm going to change the order a wee bit, actually, and do D before C, but let's start anyway with A. The initial momentum of the mass, well, it's not moving, so P1 equals 0 kilogram meters per second. You can do your MV calculation if you want. The final momentum is MV, it's 50 times 3, 150 kilogram meters per second. And then let's say I'm going to jump to D, and the impulse equals the change in momentum, which is 150 minus 0 is 150. Now the units of impulse are equal to the units of momentum, so you could either write that as kilogram meters per second, or you could write it as Newton seconds. Okay, they're both identical. Then I'm going to go back now and do C, and we know that impulse equals Ft, and we now know that that's 150, and we know that applied for 2 seconds. So F equals 150 divided by 2 equals 75 newtons. Now all of these are vector quantities, so I do to be careful about remembering. Doesn't in the question really specify anything about directions. Everything is actually just going in the one direction. But if we don't know, we're going to say in the original direction or in the opposite direction if we end up with a negative sign. So, second worked example, this graph shows the force varying when an impulse of 500 Newton seconds is applied to an object, calculate the maximum force. So for this we're using the idea that impulse equals area under FT graph. So we know that the impulse is 500. The area under the FT graph is a triangle. It's not a right angle triangle, but it's still a triangle, so it's still a half base times the height, which is a half times 10, and our height is F max. 500 equals 5 times F max, and F max equals 100 newtons.